In this lecture, I'll talk about what we are going to design in this course, which is a custom, fully functional carrier board for the LattePanda Mu compute module. If you ever worked with a single board computer, like a Raspberry Pi or a Jetson Nano, you know that the compute module is only part of the story. What really makes the module usable is the carrier board. The board that provides power, connectivity, and all the interfaces that let it communicate with the outside world. That's what we are building in this course. The LattePanda Mu is a compact, high-performance x86 compute module based on Intel's N100 processor. It's designed to deliver desktop-class performance in a small, modular form factor. However, on its own, it can't do much. It has no standard ports, no power input, and no way to connect to displays, USB devices, or networks. All of that functionality comes from the carrier board. The carrier board acts as the bridge between the compute module and the real world. It brings out the module's interfaces like PCIe, HDMI, USB, and Ethernet and makes them usable through standard connectors. In this course, we'll design such a carrier board from scratch using KiCad, following professional workflows for schematic creation, PCB layout, and verification. Our project is based on the light carrier reference design provided by LattePanda, but is not a clone. It's an original custom carrier board designed from the ground up. The purpose of this design is twofold. First, to create a real working carrier board that you could actually manufacture and use with a LattePanda Mu. And second, to create a design that's educational. I've simplified the layout where possible and focused on the parts that are most valuable for learning. How to design stable power delivery networks, how to route high-speed differential pairs, and how to organize large schematics logically in KiCad. Let's take a closer look at what this board includes. It starts with power inputs and regulation. I've implemented two input options, USB-C PD port and a battle jack connector. These feed into a custom designed power distribution network that generates both 5V and 3.3V rails. I've also included power and reset buttons and a battery connector for backup power so that the board can support embedded applications that require reliable startup and shutdown. Next, there's display and connectivity. The board includes a standard HDMI output for video, USB 3.0 and USB 2.0 ports for peripherals, and gigabit Ethernet through the Realtek RTL8111H controller. These provide all the I/O you need to turn the LattePanda Mu into a compact desktop or embedded controller. I've also added multiple GPIO headers. These headers expose the general-purpose I/O pins from the compute module, allowing you to connect sensors, actuators, or even external microcontrollers. These make the board much more versatile for prototyping and experimentation. And finally, I've included a CPU fan connector with PWM control and simple power and reset circuits that can be easily understood and replicated. Each subsystem demonstrates a practical design principle that you can use in future projects. I also want to talk about the design choices that made this board practical to build and ideal for learning. One key decision was to omit the PCIe X4 interface. In the reference board, PCIe adds significant routing complexity and increases the board size by a little. By removing it, I reduced the unnecessary difficulty while still preserving the high-speed design challenges of USB 3, HDMI, and Ethernet. This trade-off makes the course more focused and achievable without losing educational value. Every part of the design, schematic, and layout has been done manually. There's no auto-routing and no reused sub-circuits. Each connection, via, and footprint placement is deliberate, so you can see exactly how a professional KiCad workflow unfolds step by step. I also redesigned the shape of the board, moving components to new positions that make routing more efficient and logical. And this shows how mechanical constraints and user preferences influence PCB layout. Finally, I've added extra GPIO headers to increase flexibility and experimentation potential. That's something that the reference light carrier doesn't provide. Once the design was complete, I've done the verification using NextPCB's DFM application. DFM, or Design for Manufacturing, is the process of ensuring that the board can be produced reliably by a PCB manufacturer. The DFM tool checks for issues like trace-to-trace clearances, annular ring width, via sizes, solder mask alignment, and copper exposure. By running this analysis, we can confirm that our board complies with real-world fabrication limits and is ready for production. This is a key step in every professional PCB workflow, and you learn how to interpret DFM results to ensure manufacturability. In this slide, you can see the differences between the reference design, the light carrier for the LattePanda MU compute module, versus the custom carrier board, which we'll design in this course. The version that we are working on in this course trades some of the original board's complexity for better visibility and control over every part of the design process. It's really not about copying the manufacturer's work, it's about understanding it deeply and then using it to build your own version of the carrier board. I've structured this design for teaching and mastery. You learn how to create a schematic with clear hierarchy and documentation, how to lay out high-speed interfaces while maintaining impedance and ground integrity, how to apply best practices for power distribution, decoupling, and copper pores, and how to verify the design using DFM tools before manufacturing. And I've designed this course so that by the time that you complete it, you'll have the skills and workflow discipline to design any compute module-based board, whether it's x86 like the LattePanda or an ARM-based design like the Raspberry Pi compute module series. Now, as far as the deliverables are concerned, at the end of this course, you'll have a complete KiCad project, including schematic, layout, and fabrication files, a design that can be sent directly to a PCB manufacturer for production, a working understanding of the trade-offs that define modern compute hardware design, and most importantly, the confidence and methodology to work on your own advanced board projects. To summarize, in this course, we are not just following a schematic. We are building a custom high-speed carrier board that's both educational and manufacturable. Every decision, from omitting PCIe to verifying with DFM, are made to help you focus on what truly matters in modern PCB design. And as an added bonus, I left in all of my mistakes, which of course I fixed. In the next lecture, we'll look at the LattePanda light carrier reference design in detail. We'll analyze its schematic, layer stack-up, and component organization. And we'll see how we'll adapt those ideas into our custom implementation.